Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today my guest is from Mellanox. We have Gilad Shainer. He is the VP of Marketing at the company. Gilad, how are you doing today?
I'm doing great. How are you, Rich?
Well, great. I haven't seen you for a couple weeks now since the Switzerland conference, but I thought we'd use this chance to catch up on what's up with Mellanox. So what's the news, Gilad?
Sounds good. I think there is multiple new announcements that we have released around new product lines. We also released some performance comparisons on applications between InfiniBand and the Omni-Path alternative. So I think there is a lot going on, and I'll be very happy to go over with you on some of the announcements and some of the information that we have made public.
Well, terrific. Well, Gilad, I brought your slides up. Why don't we start there, and then we'll do a Q&A at the end.
Sounds great. So I'll start with slide number 2. And I think this is something that the industry is already talking for quite some time already. Definitely Mellanox is also part of the industry trend on moving from today's CPU-centric architecture where you limit the application, so everything essentially to run on the CPU, to a co-design architecture, which gonna break the bottlenecks of today and basically create synergies between the different hardware components and synergy between the software and the hardware, and deliver a greater application performance by using more intelligent elements which distributed across the entire data center. And in our part, for the Mellanox part, Mellanox is bringing more and more intelligence to the network. And the network becomes the new generation of coprocessors by providing in-network computing an ability to accelerate the applications. And one of the key things here to enable the improvement in performance is basically to start working on a data when a data moves. Today, when you wait for the data to reach the CPU before you can do anything on it, you lose a lot of performance capabilities. And we know that the CPU frequency is not getting faster anymore, therefore you cannot really accelerate the process. And the only way to accelerate the process is by working on the data of the process as the data moves. And this provides a great performance advancement, and this is the new architecture that will be used for the next generations of high-performance computing systems. So going to slide number 3, and this is one simple example. If we look 10 years ago, the network components or the latencies of the network components was in the tens of microseconds. And at the same time, the communication framework latencies, the latencies of, for example, MPI collective operations or any other complex operations were in 100 of microseconds. So the network part was pretty much an important element in that, in the overall latency. And throughout the years, there was a lot of focus on reducing the network latencies. And today, the network latencies are in 100 of nanoseconds. Mellanox InfiniBand switch has less than 90 nanosecond latency, which is the fastest switch in the market. The InfiniBand adapters latencies are in the range of 100 nanoseconds. So we saw a huge reduce in the latencies of the network functions. On the other side, if we look on MPI collective operations or overall the communication frameworks, today we're in the tens of microseconds. It's 10, 20, 30 microseconds. So now there is a huge difference between those two sides. So look into the future and try to see how can we further reduce the latencies of the network operations. And if we look on the network solutions, if the switch or adapters, those are already in 100 nanoseconds and less. So even if you continue and reduce the latencies of the adapters and the switches by doing multiple things, and you will be able to reduce another 10, another 20, another 30 nanoseconds, compared to a 20 microseconds, that's become negligible. So the real solutions to actually continue in reducing the application latencies is not by taking down another 10 or 20 nanoseconds from the network products or hardware. It's basically by looking into the algorithms being used by the applications and start to map those algorithms on any active component within the data center. And once you do that, and basically start working on the data when the data moves, so execute algorithms today on the adapters or on the switches, you can go and make another 10x of performance improvement. And that's how you're going to take the tens of microseconds of today and get it down to 1 or 2 or 3 microseconds. So that's the key thing. The key thing is not to focus on the pure latency of the switch or the adapter. The key thing is to bring intelligence to the network, make the network the new generation of coprocessors, and with that you will be able to get another 10x improvements in the application runtime. So that's what we have been doing. And moving to step number 4, Connect X4 is the latest InfiniBand EDR adapter from Mellanox, which also serve as the Ethernet NIC as well, providing bandwidth capabilities of 10, 25, 40, 50, 56, and 100 gigabit per second. It delivers 150 million messages per second, but more important, it has a lot of offloading capabilities. So moving algorithms from the CPU to the network adapter. Switch IB2, that's the latest switch from Mellanox. When we announced it, we call it the world's first smart switch, because it's the first switch that can actually manage and execute MPI or SHMEM-PGAS collective operations on the switch itself. And with that, we can make a 10x performance improvement for collective operations, which is not something that you can do on the CPU anymore today. We also offer a Spectrum switch, which is a 10, 25, 40, 50, or 100 gigabit Ethernet switch that does deliver great performance benefits compared to alternatives in the market. And to connect everything, a family of LinkX transceivers, active optical and copper cables that provide a very reliable and robust cabling infrastructures to connect between the switches and the adapters. Going to step number 5, one of the things that was missing so far in the InfiniBand offering was an InfiniBand router. So you can see here a diagram that is taken from the InfiniBand specification, where router is an entity that enables to connect between multiple InfiniBand subnets. And there is multiple reasons why a router is needed. One of them is that InfiniBand subnet can connect up to 40,000 nodes in one fabric. And if you want to connect more than 40,000 nodes in a native InfiniBand fashion, you need to bring an InfiniBand router. And then InfiniBand router enables you to connect up to 2 in a power of 128 nodes, which is basically unlimited. That is one reason. The second reason is that router is the most efficient solutions to bring capabilities of isolations between different InfiniBand networks. So you can bring isolation between InfiniBand storage and InfiniBand compute, or isolation between different compute elements. Each one of them will have its own subnet manager, its own configuration, its own management, but essentially the entire system will have a native InfiniBand connectivity all across the system. So that's another reason for an InfiniBand router. And a third advantage is the ability to connect between different topologies. InfiniBand, in a sense, is the first SDN fabric in the market, which provides a rich capabilities to build any kind of topology. If it's a fat tree or torus or mesh or dragonfly and so forth. And if you want to build variety of topologies and be able to connect them together, the most effective way is to do it with InfiniBand router. So with the continuous expansion of InfiniBand, not just in HPC, but even broader than HPC, into Web 2 and cloud, there is more and more need to bring isolations, to bring capabilities of connecting between different topologies. And in the long future, if we look on the exascale and beyond, we assume that you also be able to connect, or you will need to be able to connect more than 40,000 nodes in a single data center. And therefore, the need for InfiniBand router becomes something that we saw a strong request or demand from the high-performance computing users and beyond of that. So recently, and moving to slide number 6, we announced a new family of products that deliver InfiniBand router capabilities. So now we have InfiniBand routers as part of the InfiniBand offering. The first box is a 1U box that can connect up to 6 different subnets in 1U box. And of course, people can deploy multiple of those boxes within their InfiniBand infrastructure and to be able to connect multiple subnets and to expand their InfiniBand data centers to meet their needs. So we were very happy with the new InfiniBand router solution. We have started shipping that to first customers, and we expect to see further usage and deployment of the InfiniBand router. Going to slide number 7, just one example of one of the recent announcements in the high-performance computing systems. NCAR will deploy the next system utilizing Mellanox EDR InfiniBand solutions. Believe that the InfiniBand router is also part of their system to be able to provide isolations between the storage and the compute, for example. And that's a very nice evidence of continuing usage of InfiniBand to drive the next generation of systems and to enable the next generation of performance improvements for the workloads in high-performance computing. And in slide number 8, you can see some reasons of why InfiniBand EDR is something that is being deployed more and more. A variety of application examples. If it's OptiStruct from Altair, or WRF for weather simulations, or GROMACS, or Fluent, you can see that even on a small scale, InfiniBand EDR provides up to 63 higher performance versus FDR. Some of that because of the increase in throughput, and some of that is because of adding more and more intelligence to the new generation of InfiniBand, more algorithms being run on the network, enabling applications to actually run algorithms on the data when the data moves. There are also some examples from HPCC benchmarks, and here you see 68% improvement and all the way to 80% performance improvement on a variety of systems. Some of the performance here was tested by Mellanox. I think the majority of the examples here actually coming from our customers. So it's very good to see evidence from our customers on the performance advantage that EDR brings to their workloads. So going to slide number 9, there is always the debate outside of offload versus onload, which means an offload architecture for the interconnect versus an onload architecture for the interconnect. And slide number 10 gives a very high-level summary. Basically, there are two options or two architectural options to build an interconnect. One of them is an offload architecture, and that's something that Mellanox believes in the day one, and all of Mellanox solutions are based on that architecture. The idea here is that the network should manage and execute all the network operations. So you run the transport, reliability, making sure that the data arrives correctly, and so forth within the network, and instead of running that on the CPU. Main reason is the CPU is there for actually running applications and not manage network operations. and not creating network packets and not running the transport. And by moving those elements to the network, you can increase the CPU efficiency by 30, 40, and 50%. That was one reason. The second reason is that as we now go through the co-design architecture, it's even become more critical to start running more and more algorithms on the network elements and not on the CPU because this is the only way to actually get to the performance improvements that we need. So now we have several elements or several algorithms from MPI that actually runs on the network elements. And as we move forward, we'll see more and more of the MPI actually runs on the network adapters, on the network switches. Now, it does require more R&D investment, but the return on investment here for the data center is huge. And that's why we're seeing over and over that an offload approach wins the onload approach for every generation of products. The other approach is an onload approach, which means a CPU-centric approach. The network needs to do nothing besides of just moving data, and everything must be executed on the CPU. That means that the CPU is responsible for everything. You don't have acceleration engines. You don't have RDMA. And we all know that RDMA today is a key for multiple applications and definitely for storage. So everything needs to be done on the CPU. Reason is why to do it is because it's easier to create network products. But on the other side, you just eat a lot of the CPU cycles. So you dramatically impact your data center capability and increase the cost of your data center. Slide number 11 put one of the main claims that companies doing onload products were used to drive, which is there are too many cores out there. You know, we live in a multi-core environment. There are so many cores out there, and you probably don't use all of those cores, so why not use CPU cores to do the network functions and so forth? But this is no more than a FUD. You do pay for every core you buy. And I have example here on an Intel Haswell CPU where you see the cost difference between 10 cores, 12 cores, and 14 cores. So just move from 14 cores to 12 cores on a dual socket server. The cost here is more than $1,500. So every core is expensive. If your application does not need 14 cores, then buy 12-core CPU. It's going to be much more cost effective and you can get higher frequency of CPUs. The cost delta of every core on a server, it's more than the interconnect cost. So there are no cores for free. Every core costs you a lot of money, and people should design their system to meet their applications. So there are definitely not free cores that you can use it for doing something else. No, you are going to use every core that you buy for running your application. Slide number 12, start giving you for the first time, some performance examples, real applications performance examples that compares between EDR InfiniBand, which is an offload architecture. It's a smart interconnect. Drive the network functions to be managed and executed by the network. Bring further capabilities to accelerate applications and free CPU cycles. Versus the alternative, which is the 100 gig Omni-Path approach, which is complete onload approach. It's based on the QLogic TrueScale, which is based on Pascal InfiniPath in the past. All share the same common architecture of running everything on a CPU. And here you see a clear difference. And it's even a small system size, so you don't need to go to a very large scale infrastructure. On a 10 nodes, and running Win2K applications, you can see that there is a 35% performance improvement using InfiniBand versus using Omni-Path. And the gap increases with the system size. So, and this is a major difference in application performance in your data center capability. Now, going to slide number 13, I'm keeping the same EDR and Omni-Path numbers, but I'm also adding FDR. And in this case, you see that even InfiniBand FDR delivers better performance than Omni-Path, running at half of the bandwidth speed. And the reason, again, is the offloading capabilities. So if you free the CPU cycles, if you run algorithms on the network, you can run application faster. And this is the important part. Even FDR can deliver higher performance versus Omni-Path. Slide number 14 takes another application example, which is Quantum Espresso. And here it's the same thing. Here we're seeing 42% performance improvement on 10 nodes, and the gap increases with system size. Again, a clear evidence of an offloading approach versus an onloading approach for running HPC applications. Slide 15 present the two last examples for now. Two cases of LS-DYNA. One of them is using the Neon Refined Revised benchmark, which is a smaller data set benchmark, and the other one is 3 cars, which is the larger data set benchmark. And here you see a difference between 48 to 63% performance between EDR and Omni-Path. And one thing also to mention here is that in the small case, the network becomes more and more important where you have more and more servers. Basically, you are sending a lot of small messages, and the network becomes the critical part in the performance of the application. And for that case, you can see that Omni-Path does not scale beyond 10 nodes. And on the other side, InfiniBand continues to scale. And not less important, if you examine the performance results here, you can see that in both cases, InfiniBand at 6 nodes provides same or higher performance versus Omni-Path at 12 nodes. So with half of the compute infrastructure, InfiniBand delivers higher performance versus Omni-Path. And again, that shows a clear advantage of an offloading architecture versus an onloading architecture, and also provide a very good example of why people should look on the entire data center infrastructure and make sure that they bring a balanced system. Because in one case, you might need to buy 12 servers and use an onload approach to get the performance that you need. But instead of that, you could buy half of the compute servers and use InfiniBand. So there is a huge, not just performance advantage, but cost advantage, both on OpEx and CapEx. So going to slide number 16, and here I want to talk a little bit about how do you need to look on the data center return on investment at the end of the day. And it's important to look on the entire data center components when you build a new data center, to make sure that you get the highest application performance or the highest return on investment. So on the left side, if we're looking on using an onload approach, for example, Omni-Path, let's say that you bought a compute systems in a worth of $1 million. And you got an onload network product here, for example, Omni-Path, at 0 cost. It was free. So the total cost of your infrastructure was $1 million. And let's take a very conservative approach here and say that the onload network here takes around 30% overhead from the CPU. And this is a conservative, we look on examples that were much higher than that, but let's take a very conservative approach. So 30% of the CPU is wasted on non-applications work. So therefore, the compute worth or the return on investment is $0.7 million. Now, on the right side, let's assume that you bought the same compute systems at $1 million, and you actually paid for InfiniBand, which was $150,000 a year. So your total cost was 1.15. The CPU overhead with an offload capabilities is 0. So the compute worth back to you is $1 million, which means higher ROI. Now, you can definitely say that, well, on one side I pay 1 million, and on the other side I'm paying 1.15 million, so I'm paying more. And I can say that's fine. Let's assume that you want to get the same 0.7 million back as return on investment from compute capabilities. So having that number in mind, if you're going to buy InfiniBand, your entire system is going to cost you 0.8 million. So 20%, even that you are getting the network for free with Omni-Path, you can get the same performance, if not higher, with 20% less of your total data center expense. And that difference is much higher than the network difference. And that's important to keep in mind, and that's why I also demonstrate or show you the several application examples. Paying for InfiniBand and bringing that into a data center results in a more cost-effective data center. And that's something that we see from multiple user examples, and that's one of very good reasons why offloading architecture is the right one. So slide number 17, a little bit background of Omni-Path. Omni-Path was born in 2005, more or less. Pascal as a company brought an alternative for Mellanox InfiniBand, which called InfiniPath. It was a completely onloading approach. So no offload network running at 20 gigabit per second, tried to compete with InfiniBand DDR, which didn't really work out. QLogic has acquired InfiniPath technology and released the TrueScale product line, which was based on the same architecture, with just moving the SerDes speed to around 40 gigabit per second and compete with QDR. Didn't really work out. And Intel acquired TrueScale, changed the name to Omni-Path, moved the speed from 40 gig and 100 gig, but it's the same onloading approach. It's the same thing. So over time, there were a few systems here and there that either Pascal or QLogic won. Mellanox continued to have the lead on the high-performance computing systems because of the performance, because of the efficiency, because of the scalability, because of the return on investment. And we believe that we'll continue to show that versus the Omni-Path alternative. It's also important to note that earlier this year, we have made the first demonstration of running silicon photonics at 50 gig per lane, which is the first step in providing a complete solution for InfiniBand HDR to run 200 and 400 gigabit per second. And we continue on track to provide those solutions in the 2017 timeframe, which will continue and maintain the Mellanox one generation ahead advantage over the competition. Slide number 18, some numbers that released by the competition from Omni-Path. What we see here is basically putting higher number out there versus actually number that people will be able to measure and reducing expectation over time. At ISC 2015 last year, Intel announced that, for example, their solution will deliver 160 million messages per second, which was claimed to be 6% higher than Mellanox, where Mellanox providing 150 million messages per second. It was also claimed that the switch latency will be between 100 and 100 nanosecond, which is 23% lower than Mellanox, while Mellanox is a 90 nanosecond switch latency. Earlier this year in February, Intel released a different set of numbers. Actually, they claimed that they estimated the message rate to be between 75 and 86, and they were measuring 108 million messages per second. And this is definitely not the 106 they claimed before. And just a week ago at IDF China, Intel released another set of numbers where now they claiming to have 105 million messages per second on the new Broadwell CPUs. So the performance expectation does reduces over time, But it's also interesting to see that they're putting a range of message rate, which typically you don't see. You actually see a message rate that you can achieve. So the range may imply jitter, but those numbers are definitely not in par with Mellanox numbers. Mellanox drive 150 million messages per second, for example. So even on a low-level benchmarks, Mellanox solutions have the advantage, and definitely when you go to the application cases, which we discussed. So slide number 19. So overall, when you compare InfiniBand to the alternative of Omni-Path, we're seeing multiple application cases demonstrating between 35 to 63% performance advantage on a low scale of an infrastructure. And as the number of servers increases, the gap increases as well. InfiniBand continues to enable the highest system performance and can achieve higher performance on half of the servers compared to the alternative. And it's basically the only interconnect, if you look comparing to the alternative, that scales with system size, and we see the performance advantages of InfiniBand continue to grow. So in summary, we definitely see clear advantage for an offloading approach. First, it delivers much greater return on investment, free CPU cycles, and enables you to get better application performance. The second thing, offloading is the key for the next generation of platforms. The ability to start running algorithms, NP algorithms, for example, on the data, when the data moves, is critical to achieve performance improvements over time. And then the last one is that Mellanox continue to drive the technology speed. We already demonstrated the first element of 200 gigabit per second, 400 gigabit per second, and continue with our schedule to release InfiniBand HDR in the 2017 timeframe.
Well, great, Gilad. I mean, you've been talking for a while here. Now I apologize. I wanted to let you go through it all. How is this message resonating with your customers, this ideal of offloading versus online?
I think many customers understand the difference between onload and offload. They understand the benefits of InfiniBand. They also understand that it's worth even paying more for InfiniBand in order to build a balanced system that can essentially deliver the right performance for the users.
Yeah.
So we do see it go very nice out. Mellanox, we do expect that Intel Omni-Path will win some systems here and there, as the competition in the past. But we continue to drive technology from our side, advancement to the performance, and we continue to work with our users to enable them to leverage from InfiniBand for achieving their goals.
Well, I wanted to ask you about the user side, Gilad. Back to slide 12, the quantum mechanical simulation. I'm just curious, does the user have to choose onload versus offload with their code, or does something else intervene there and compile it for you and make it run efficiently on the architecture?
Yeah, the users don't need to do anything.
Yeah.
Basically, the network infrastructure set if you have an offload capabilities or non-offload capabilities, and if you do use InfiniBand, then MPI framework knows how to take advantage of it. And for anything is basically in the MPI or the driver level, and from application perspective, you just need to run them and enjoy the greater performance.
And looking out to the future, Gilad, of course, CPUs just tend to have more and more cores. Is that going to help your argument from your side, or is it going to hurt?
No, it's the reason that you bring more cores is that instead of accelerating a single process, you want to run more processes in parallel.
Yeah.
Right. You cannot get the frequency to be faster anymore, so you start running more in parallel. Running more in parallel means that you're running more jobs, that the CPU has more to do. There is more load on the network. And if you're going to force the CPU to dedicate it part of the time to do non-application perspective, first, you use CPU efficiency, and the more cores, the bigger the loss. The second thing is that you can create jitter issues within the systems, and you take processes out of balance, which also impact the performance. And it's more important even to note that in the CPU accelerators, if it's night corner or night landing or NVIDIA GPUs, there are more and more cores that enables you to run things more in parallel, but those cores runs in a slower frequency. So when you reduce the frequency of the CPU, the amount of load on the CPU to drop the network becomes even more critical and much bigger. And we see evidence that running CPUs in frequencies of 1 gigahertz or 1.1 gigahertz or 1.2 gigahertz actually reduce the network performance if you're using an onload approach by almost 50%. So it's not that just it's important to have an offload when you have more and more cores. It's also it's become critical to have offload when using the many core devices that runs in much lower frequency.
Well, great, Gilad. You know, it's really interesting to watch this debate go forward. And I know for Mellanox, you know, offloading has been something you've been using from the start. And I want to thank you once again for coming on the show today.
And I want to thank you very much, Rich, for giving me the opportunity to present.
You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.